To session 6 of ML Model Eval. Today we're going to cover two very important things when it comes to building your model, which is, hey, we have all of these parameters. We have all these potential knobs and dials that we can twist and we can tweak and we can turn when it comes to building a machine learning model. How do we know when we hit the sweet spot? Like, how do we know when we built a really good model? Obviously, we have metrics and evaluation metrics to do that, but what's the actual process for robustly testing and training these models? So we're going to talk about hyperparameter tuning and grid searching. So hyperparameter tuning and grid searching are going to allow us to discover things like let me just draw an XY axis here. Let's say on the Y axis here we have loss. And let's say on the X axis here we have our parameter that we're searching over. Maybe it's depth of a tree. Okay, we have a random forest and we're searching across some different tree depths. Maybe we have a depth of 1, we have a depth of 5, we have a depth of perhaps 15, we have a depth of 30 maybe. This is clearly not a proportional chart, but bear with me here. And then on the Y-axis we have loss. And is loss something that we want to maximize or minimize? Do we want a high loss or a low loss?
Low
loss, absolutely. So 0 would be fabulous if we had a loss of 0, and then this increases as we go up. So what we want to do, I'm going to get a different color, is we want to search across these parameters and see how these parameters affect our loss. And basically, we're going to train a model at each of these points, and maybe more points. Sorry, that's supposed to be on the line. Maybe there's more points in here. And clearly, the model that did the best would be this one. This was our best model. This is our best model because it had the lowest loss across all the parameters that we trained on. So we trained on a series of 1, 2, 3, 4, 5, 6, 7 parameters. We have 7 circles on our graph here. So we trained across 7 different parameters, 7 different values for our parameter, which was max depth. So 1 parameter, 7 different values for that parameter. And we found that the best model was this one right here. That's hyperparameter tuning. What we did is we had a hyperparameter, max depth, and we tuned our model. We found where the sweet spot was. Now, what if we had more than one? What if we had another dimension here? Well, we're going to go XYZ dimension here. And we had more ticks going in this XYZ dimension. And instead of max depth, this is n estimators. And we want to train a model that's a combination of all these things. So this parameter, and we'll start to get like a 3D shape in here maybe. That's like a combination of each of these parameters. I'm not describing this poorly. Maybe I should draw this out. What's going to happen is we're going to have n estimators. And we're going to have max depth. And we're going to have some type of performance metric. Remember, we talked about a lot of different performance metric. This is up to you to choose the performance metric. Perhaps the performance is accuracy, or perhaps it's F1, or perhaps it's precision, but we're going to have some type of performance metric. And the nuance here is that if we're interested in searching over, we said let's 7 different values for our max depth. So I'm going to call MD. So MD, let's say we searched over, oh, that looks about to be 1. Maybe we did 3, 5. Did 1, 3, 5, 10. I'm going to run out of room here, aren't I? 4, 1, 3, 5, 10, maybe 16. 20 and 35. Okay. Let's see if we fit this on here. All right, 35. And let's say that we only want to search over 2 parameters for loss, or for n estimators. I'm going to call NE. For NE, let's just say we want to do 100 and 200. The impact of this, what I'm talking about here, is when we do a grid search. When we do a grid search, if it's a random grid search, we have 7 parameters here. We have 2 parameters here. And we're going to have to take something called the Cartesian product. So this is going to be a linear combination of these 2 things. So we're going to take 1, 3, 5, 10, all the numbers here. And then we're going to match all of those with 100. So n estimators is 1, max depth is 100. I did that backwards, didn't I? I apologize. I should have started with n estimators. N estimators is 100. Max depth of 1, 3, 5. We go through all of those numbers. And then we do max depth is 200. And then we go through all the numbers again. 1, 3, 5. What we're going to end up with is 2 times 7, which is 14. We're going to train 14 different models. And we're going to have a performance value, 9.7 for this one, 9.9 for this one, maybe 5.3 for this one. It didn't do really well on that combination of 100 and 5. We're going to have a performance value associated with each of these models. That's a grid search. So we're running a grid search over the combination of these parameters. Okay, so we'll talk more about that. We're going to talk about how to actually, no, let me tee this up. Okay, so that's hyperparameter tuning and grid search. That's the first topic that we're going to talk about today. How do we've got all these knobs and dials and things that we can twist and refine. How do we know when we hit the sweet spot? The other thing that we're going to talk about today is maybe I should have called this modeling methodology. We haven't touched on modeling methodology, and I think it's very, very important. So we're going to talk about train test split. What is train test split? Why do we do train test split? And then through that, we're also going to look at the lens of cross-fold validation. And we're going to dive particularly into K-fold cross-validation so that you guys can understand how that works. But we're going to go through modeling methodology, just like we have the scientific method. So data science is the word science is in the term data science for a reason. And it's because we are performing experiments. And in order for these experiments to be valid, we have to have methodology that we lean on and we leverage. So this comes down to making sure that we're doing things like not data snooping, making sure that the metric that we're creating is one that is generalizable to unseen data, that broadcasts to the application that we're trying to apply it to. All of this will fall under the realm of model methodology. All right, let's dive in. Let's talk first about hyperparameter tuning and grid searches, essentially. Why do we need to do hyperparameter tuning? So here's the problem statement that we were talking about before. We've got a tree here. It's not even a random forest. We have a decision tree. Let's back up from random forest. Let's just talk about decision trees. We're training a decision tree model, and we have 3 different max depth parameters. And we want to identify what is the max depth that we should set our tree to for our data set that we're training it on. So what we do, a very natural thought to have is, well, let's just train the decision tree over each data set. And then, let's just train each decision tree over our data set. And then we'll compare for our data set which tree performs the best. So we have our data set, and we're going to give it to each tree. We're going to give it to this one, we're going to give it to this one, and we're going to give it to this one, and we're going to say who did the best. So this is truly a competition. And this tree had a max depth of 1, this tree had a max depth of 2, and this tree had a max depth of 3. And we set our performance metric to be F1 score. We have to set a metric to determine how do we know which model is performing the best. And perhaps I should have put accuracy on here and said and showed that, maybe if we made it accuracy, and this was 0.5, maybe this one was 0.6, and maybe this was 0.4. If we had set it to accuracy, we might have chosen a different hyperparameter. We might have chosen a max depth of 3 instead. But we chose our score, our performance metric, to be F1. And because we chose the performance metric to be F1, we found that this was our best performing model. This was our best performing hyperparameters on this model algorithm, our model algorithm of decision tree. So this is how we chose this one as our parameter. We can generalize that to a larger set of parameters, and we can generalize that even to comparing things across, comparing different models, modeling algorithms across that onto that data set. This is hyperparameter tuning. But when we're talking about one algorithm, like decision tree or random forest or linear regression or logistic regression or neural networks, and we're trying to tweak the knobs that come with that, you go to the sklearn documentation for the algorithm, you see all the different parameters that you can pass to that object function. Those are what we're talking about. So hyperparameter tuning refers to the process of optimizing the hyperparameters of the machine learning model to improve the performance. So we're trying to figure out what does optimizing mean? Optimizing just means we're trying to figure out which one is going to drive the best performance relative to the performance metric that we've chosen. So what's the difference between a parameter and a hyperparameter? I'm going to take a drink of water here. There's not, this is a bit of a nuance, and I think the nomenclature has come a long ways in the last couple of years, that it's become more defined. But when we talk about parameters, typically, sometimes these things are used interchangeably. Honestly, as you're reading documentation, people say, oh, what are the parameters for the model? And they'll actually be the hyperparameters. So they're not, this isn't set in stone, but generally, when people say parameters, they're typically referring to the weights of a model. So remember we had this neural network last course that we built, and it was fully connected neural network, all the nodes, boom, 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 right? Okay. Something to that effect. And we had weights and biases. Remember, this was our input layer. This was I. And remember, each of these nodes represented kind of a y equals mx plus b in them. So we had a sigmoid function that was transforming our output, taking in these weights. It was y equals beta sub 1 plus beta sub 2 plus beta sub 3 plus our bias of our model. So in each of these, we had our I think we really simplified that to the weights times the bias, WB, for each of these. So we have 1, 2, 3, 4 going to this node. We have 1, 2, 3, 4 weights going to this node, plus the node has a bias in it. So there's 5 parameters in this node. There's 5 parameters in this node. We have 2 weights going to this node, plus a bias. So there's 3 parameters in this node. So now we have a 13 parameter neural network, right? Okay. Somebody correct me if I got that wrong, but I think this is correct, a 13 parameter neural network. If we look at the large language models of the world today, they have billions and billions of parameters. So when you see and read about the large language models, about the AI models on the internet, and it says, hey, these parameters that are in the model, that term parameters is referring to the weights and biases, the actual learned parameters through back propagation that were learned by the model when you're training it over the data. So these are the weights and biases. When somebody says, oh, OpenAI released a new model and it has a billion more parameters, has a billion more weights and biases. I'm just going to put B for bias. Okay. So hyperparameters, on the other hand, are not directly learned from the data during the training process. So these are set prior to training. That's an important thing to say. So when we build this neural network, we are giving hyperparameters to the neural network. We're defining how many nodes there are. We're defining how many layers are in the neural network. We're defining whether it's a fully connected neural network. We're defining the architecture of the network. We're defining the activation functions of the network. Not everything is as a sigmoid function. We could use a ReLU activation function. There are a lot of different activation functions that we could use. We're deciding what's the output transformation on this output layer. How are we transforming the probabilities? Is it a multi-class problem? Is it a binary classification problem? So is it a softmax transformation? These are all hyperparameters that we put into the structure of our neural network before we start building it. So that's what we're talking about when we're talking about hyperparameters. So you might build 10 different neural networks, 20 different neural networks, and because they're defined with different hyperparameters. And then each of those go through their own training process that defines their own parameters, their weights and biases associated with that neural network. Okay, let me pause for just a second. This is probably more important than some of the next slides and contents. So I just want to check for understanding here. Is this resonating with you guys? Hyperparameters versus parameters. Okay. I'm tempted to pull up sklearn. Let me give one more example that's not a neural network, one that we're maybe more familiar with, linear regression. Okay. Linear regression, as you guys remember, it's a regression model, so we're predicting scalar output. We can use this to predict the price of a house, for example, and we talked about this as our y equals mx plus b problem. Equals mx plus b, and then eventually through the course we evolved our y equals mx plus b to be y equals beta sub naught plus, I don't know why I made that a little b, beta sub naught x sub 1. No, not x sub, sorry, that's the bias. Beta sub naught plus beta sub 1, x sub 1. I'm just going to do 2. So plus, that's supposed to be 1. I was thinking about the next thing. Beta sub 2, x sub 2. Etc. However many betas. X is the value, these are the features. X is the features. So this is like number of bedrooms, square footage of house. Beta, that's what we're learning. That's the parameter. So this is the parameter in the model that we're actually learning. This is like every 10,000 square feet you add to your house, or I'm sorry, I said that backwards. Every bedroom you add to your house is worth another $10,000 on your house. Maybe beta would be 10,000, and the what you're multiplying it by is number of bedrooms. So the learned weight here, the learned parameter, is 10,000. So that's parameters in linear regression. What's a hyperparameter in linear regression? Would be learning rate. So if you go look at sklearn, we look at their documentation. There's a bunch of, let's just do that. I think this will help. Let's look at logistic regression. Here. In logistic regression, we go to sklearn, we look at the documentation, we scroll down, they have these parameters, which we're going to refer to as hyperparameters, just for clarity of organizing things into different categories, which humans love to do. So one hyperparameter is what's your penalty? Is it L1 regularization or L2 regularization? C is another very common hyperparameter. So default is 1, but we could search over this to evaluate different values for C. Okay. This is fun. So how quickly your model learns, the rate at which it's learning, searching the space, these things will be, oh, actually, I want to share that from here. Hyperparameters. Okay. So a hyperparameter is set before the learning process begins. It's not learned from the data, but rather it's a hard-coded specific value that we have set onto the model. We can try a bunch of different ones and see which one performs the best, and that's a grid search. But hyperparameters really control the behavior of the learning algorithm. So if we're looking at random forest or a decision tree, we're controlling max depth. We're controlling number of trees in the random forest, or N estimators. Model parameters, on the other hand, are learned directly from the training process. So if we look at you're not telling the model that it needs to use the value of 10,000, multiply that by number of bedrooms. It's figuring that out through its own mathematical process, through its algorithm. Okay, maybe this is, I did all my examples on the other slide, so I apologize. So yes, the hyperparameter versus parameter example, we talked about linear regression. Here, we talked about coefficients, weights, and intercepts as it applies to a neural network, and we talked about learning rate in terms of that being a hyperparameter that you can set in advance, which is applied to gradient descent, which is used for neural networks. Okay. One of the goals of this course, by the way, is to give you all the terminology and nomenclature that you need, at least enough of it so that you can really pioneer through the rest of the documentation and keep up with and read and learn more outside of this course. We only have a very short 4 weeks, so we can't learn everything. So what I try to focus on is how do I give you the tools to navigate beyond this course? And one of those things is terminology. And so as you're reading things, you might see the word tuning used in the context of hyperparameters. All that means is we're applying some type of optimization to search over these different hyperparameters. We're going to talk about a couple of different ways to do that. So we can search. Tuning is when we're tuning our model. We're searching over these predefined values and distributions and seeing which one has the best performance or the best outcome that we're looking for. Okay, this is just equivalent to the table that I drew at the beginning. So we have these hyperparameters. Let's say number of layers, for example, is 3 and 5. And actually, I don't quite like this because 5 should actually be tested on all the other parameters as well, not just on 256. Should really be a linear combination. I guess maybe this isn't a brute force search. This is a different type of search we're doing here. But we have different performance associated with the combination of these parameters. This is what I'm trying to emphasize on this slide, is that we have combinations of parameters here. These three combination, and it's the same modeling algorithm, and it's the same data set, but we're getting different performance. So this is how we're tuning our model. We're tuning our model because we had 85, and then we moved to 80, and then we moved to 90. So we're turning these dials in different combinations to figure out what's going to produce the best outcome here. So how do we perform hyperparameter tuning? First, we have to define our hyperparameters. So we have to tell the model what it's searching over and how many to search over. And we have to be a little careful here because things can quickly get out of hand. Then we have to choose our search space. So this is really, are we combining everything together? Are we kind of doing this random sampling, sort of like this one was doing? How are we performing that? What's the entire space that we're searching over? How long is this going to take? Select a tuning method, then we're going to evaluate the performance. Ultimately select the best hyperparameters, and then final model training. So there's kind of a nuance here when we talk about train test split. I don't know if this is the best spot or if we talk about that later. I think we can talk about that in k-fold validation, but I'll tell you the nuance now is that when we train these hyperparameters, we're actually going to evaluate on subsets of the data. So what we're actually going to do is we're going to take our data set, we're going to break it into 3 components, for example, train the same hyperparameter combination across these 3 different components, take the average, and that'll give us a more robust evaluation. After doing all that, we're going to want to retrain on the entire data set with our best hyperparameters. So we'll talk about that in k-fold validation. So real quick here, we have define the hyperparameters. Let's see, we're going to go through 6 of these. Let's see how far we're going to go here. I think we can make it to the break slide. Okay, we've got maybe 10 or so slides left. So the first thing that we're going to do is identify the hyperparameters that you want to optimize. So we have to actually say for C, we want to search over 0.1, 1, and 0.0. I put these in a really weird order, sorry, 0, 0, 1. Or we have to say for C, we want to search over 0.0001, 0.001, 0.011. I think the point I'm trying to make is we have to define what the values are, and how many of them we want to search over. How large is this going to be, and how many parameters that we want to actually leverage. There are default parameters, so for some, if not all models, most models for sure, you do not necessarily have to define that. Okay, so choose a search space. This is just a range of values of distribution. So if you saw here, I was kind of evenly spacing these out. So this is a pretty even distribution. Like we're searching, draw an XY axis here. We're searching here, and then 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 we're searching. We don't have to do that. And there's actually good evidence for why maybe not to. But we could search here, and then these three values really close together, and then one way over here. So you have to define the distribution of hyperparameters that you want to search over during training. You don't necessarily have to go every 5 when you're looking at max depth, for example. Then we have to decide how we're going to apply the tuning. So what are we going to do? Are we going to do a grid search, which is what we talked about, where we're searching through the linear combination. So if we have P1, P2, where these are, maybe I should call them hyperparameters, HP1, HP2, HP3, and we have 7 values for HP1, 2 values for HP2, and 2 values for HP3. How many models are we going to train here if we're doing a grid search? Okay, so we're going to search 7 times 2 times 2. So 14, 7 times 2 is 14. 14 times 2, we're going to have 28 models. Maybe that's too many, or maybe we have more parameters. Once we start upping these numbers, maybe we have 10, 10, 10. That gets really, really big. So we can do other methods, other techniques where we don't have to do a linear combination of all the parameters. We can use a random search. We can do Bayesian optimization. We can do gradient-based optimization. There's evolutionary algorithms. So we're talking about the basics kind of today of grid search, but there is so much more depth that you can apply and explore here. Excuse me. Shouldn't have eaten those Starbursts. Okay. And the last piece of this is that we have to evaluate the performance. Remember, we had that XY axis here at the beginning where we had the loss compared to a parameter that we were searching over. That's us evaluating the performance. So that's the final step here. Once we evaluate the performance, we can select the best hyperparameter set, and then we have to retrain our final model. So we have to take that hyperparameter set and apply it to our final model and train over our entire data set to make sure that it generalizes. I have example here. I think we've walked through quite a few examples. I think we're good. I'm kind of doing that on the slides as we go. So some of the challenges, this all sounds great, right? We've got these combinations of parameters. We can search and find the right ones. Sometimes it's really hard. There are some complications that come into play. One, which we've already touched on a little bit, and I'm sure this is the first spot that your head is going to, is that, wow, if I have a lot of parameters I want to search over, or if I have a lot of values in a particular parameter set, I want to make sure I find the right thing, then that search space is going to get really big. And we just talked on a couple slides ago, hey, there's 28 models. What if we had 10 for each of these? Then suddenly we're training 1,000 models. Somehow we went from 28 to 1,000 models. And maybe your data set's really big and each model takes a couple of minutes or maybe 45 minutes to run. How long is this really going to take? So I have a friend of mine, they were in grad school, and they were doing their final project, and they had a pretty big data set, and they were training a fairly sophisticated model that took a long time to run. And they had all these parameters that they were searching on, had it on a GPU. This was a long time ago. And they set the model to train. And they checked on it the next day, it's still running. They checked on it the day after that, it's still running. And then they got a little concerned because their thesis was coming due in the next couple of weeks, and they were wondering how long is this going to run? So a lot of these algorithms have a big O notation, a runtime associated with them. So they did some quick like back of the napkin math, and they found that the model would continue to run and train over these different hyperparameters until after the due date for their thesis. So they had to kill that and really slim down the parameters that they were putting into the model so that it would finish in time and they could read out their results. So this is important, and it's a challenge, I guess, is what I'm emphasizing here. Similar to that, a different side of the coin, something that we face is and I realize I have slides for each of these afterwards, so maybe I shouldn't be doing my story time on this slide. The next thing we face is the curse of dimensionality. It's similar to that, where once we have a lot of different parameters that we're combining, the search space between those gets very sparse. Things get really sparse and really spread out, and I have a picture that represents this well. Interactions with each other are complicated, so just because we space everything out evenly doesn't mean we have this nice gradient that we're searching through. Parameters combine in weird ways and kind of make for an uneven plane in terms of a search space. Evaluation metrics are really important, but also challenging to choose the right one. Computational resources, like I talked about in that story. Overfitting, which we should touch on, which is when you make your model almost memorize the training set. It gets too good, essentially. It's too good on the data set that you're using it on. The problem with it being too good, you might say, no, it can't be too good, is that when you put it into production, it's not going to perform well generally on the data that you see in production because it was overfit to your training data. It was really tightly memorizing what it saw in training, which is not necessarily representative of everything that it's going to see in the real world. And domain knowledge, of course. Okay, so let's walk through a couple of these. When we're talking about search space and we're talking theoretically, we know, oh, great, this is where we want to get to. This magical box. Let's say this is accuracy. So on the x-axis here, I'm sorry, on the y-axis here, we have model accuracy. So remember, this is when we want to optimize, not minimize. So we want, or maximize. This is when we want to maximize, not minimize. And because we want to maximize it, we're looking for the top of these peaks. So we're doing ascent, not descent here. So we're trying to find the tops of these peaks. And we can look at these pictures. And by the way, we have two hyperparameters, x and y axis, that we're trying to define. This is a better picture than what I was trying to draw. When I was trying to put in this third green axis here, this is what it would actually look like. We end up getting, when you move from x and y to x, y, z, we're moving from a two-dimensional plane. Now we have a 3D picture here, a three-dimensional plane. So this is the combinations of hyperparameter 1, hyperparameter 2, and the performance output. So we have hyperparameter 1, hyperparameter 2, and the performance output. And sometimes, like down here is not a good combination. Whatever value this is for hyperparameter 1 and value this is for hyperparameter 2, that's terrible. This one is also pretty bad. This one is good. So whatever this value is for hyperparameter 1 and this value for hyperparameter 2, we can map that to those axes. That's a good one. That's what we're looking for. We don't know where that is. So in reality, what this looks like, the point I'm trying to make is what this looks like to us is it's blank. There's nothing there. And what we're going to do, I'm going to put P for performance, H1, H2, is we're going to pick a few spots on this and we're going to try them. And we're going to hope that we end up picking one that's a good spot. So this, in reality, you know, if we try 5, 6, 7, our picture looks kind of like this. But if we tried every combination of every parameter that we searched for, every value across hyperparameter 2 and every value across hyperparameter 1, theoretically, we could have a map of the space. And each of these little dots on here represents another model that we train. So there's hundreds of models here. In reality, we don't have time to do all of that. And this is the challenge. This is the challenge I'm trying to emphasize, is we can't search everything in the search space. We can't search across all of these values. So when we define that the model parameter combination that we selected has the best performance, it's the best performance of the combinations that we defined. We don't theoretically know what the best potential performance could be for this model, or if we found it, unless we searched every single combination of values. Let me pause for a second. Does that make sense? Okay. The next slide is just what I was trying to draw in the upper right-hand corner here is just reality. So this is theory. In theory, we can get this like cute map, and when we're doing maybe trying to prove things out from a research perspective, we can do this. In reality, to us, it's going to look something like this. I have to cough. I'm so sorry. One moment. Okay. In reality, we're just trying these combinations, and all we have for our assessment of evaluation of this is some dot in space. And maybe we can make some interpretation about this to this or this to this, but that's not necessarily true. Like this could go way down here, or for some reason this combination could be really good and we could have a really high performance. So what I'm saying, it's not a linear line that we're drawing between these things. We can't do that. The next piece is the cursive dimensionality. So when we have one dimension we're searching across, it's not so bad, right? We have, let's call this H1, hyperparameter 1. And we're searching across these values. And you can see that we can get a pretty close spread here, right? They're pretty tightly coupled together. Once we pop that second dimension in here, wow, look how much further spread out our points are from each other. And once we pop a third dimension in there, they really continue to separate. And that's creating more space between our parameters that we don't know how well it's doing, right? That what I was drawing on that other, there's like all this area in here that is left to question how would the model perform if we did well. Where we're looking at here, it's not very much. It's just a couple of spaces of unexplored space. The more parameters that you add, the more combinations that you add. So we can only go up to 3D, but obviously you can have 4 parameters, 5 parameters, 10 parameters that you're training in your model. The challenge we face here is this cursive dimensionality. It's the sparsity of those points in that dimensional space, and that it gets very sparse is essentially what I'm trying to say. That this gets really, really hard to create. Now we have to do lots and lots and lots of models in order to actually have a good representation of the performance across that hyperparameter search space. So because of the curse of dimensionality, we can't train robustly on every performance metric. So there's different approaches that we can take here. We can get creative. We are 2 slides here from break, and I promise we'll take a 10-minute break here in just a minute. One is one thing we can do is we can use techniques to do more advanced searches. So instead of just picking spots in random space. So in this first one, we're just going to do a random search, this grid on the left here. We're just going to pick random spots in space. When I say spots in space, I mean like max depth of 15, max depth of 30, max depth of 7, n estimators 100, n estimators 200. We're sort of like throwing darts at the board, and then we're just going to see the performance across all those darts we threw at the board, and we're just going to pick the best one. So what do we have here? Final parameter hyperparameters right here. There are other techniques we can use. If you're curious, I would encourage you to learn about Bayesian search and how you can apply a Bayesian search to hyperparameter optimization. Instead of just throwing darts at the board and picking random things and having the best one come out of random, we can learn. So what if we could learn on this space and we said, oh, look, we did kind of well here. Let's move a little more this way, see how we did. Oh, did we do a little better? Well, I think we need to move a little more this way. So the question is, instead of just throwing things randomly, can we use a more sophisticated technique to navigate this plane a little bit? And yes, so we can use Bayesian, this Bayesian search. Notice in Bayesian search, there's a lot of area over here and over here. We didn't search. What happened is we tried something and it kind of worked, and we started to move towards that direction. So the final hyperparameter is here, and you can see an outcome of this is that we tried a lot of spots, a lot of combinations around this area because we found it was working. So different types of searches. This one is not using random, but instead using hyperparameter. One thing I want to emphasize is that when we look at the code and we look at k-fold validation, we look at cross validation, we're going to also look at grid search, and you're going to need this for your homework when we look at grid search. This is what sklearn is doing. So SKL. sklearn is doing a grid layout. It's doing that linear combination of all your parameters that you're inputting. And this is our performance curve that it's showing here. Another technique, you'd have to use a different package to do this. But in sklearn, we're getting this cute, pretty little, we combined 105, and then we combined 205, and then we combined 107, and then we combined 207. That's what sklearn. That's what we're going to talk about. We talk about k-fold validation. We talk about grid search. There's another technique. So I gave you 2 here. One's Bayesian search. This is a different type of hyperparameter searching. The other one is random layout. We don't have to do every combination of every parameter. We can randomly select combinations of parameters to find to search this space. So we can do a random layout here. So instead of saying 105, 107, we can say 103 and 8. And then this one can be totally different. We can do a 107 and 9. So we'll write that down. Oh, my computer's going to die. I got to plug that in. 103, just in time for break. And 8, we can do 107 and 9. And we could just see the different performance across these two things. And there's some pretty good papers out there that actually show compelling evidence that this is a better way to do it. And that the way of doing, so as opposed to do 105, 107, 100, and maybe 20. And then we're going to do 205. 207, etc. Okay, so this is kind of the standard way. This is the normal way, the out of the box way. Maybe I should say it that way. This is the out of the box way. A slightly different technique, which is pretty well supported in terms of finding this optimal outcome a little faster if you don't have a ton of compute to run, is random layout. There's some more resources here for you. Check that out. And we're going to take a 10-minute break. I have to grab a charger. So, break time. I lost my screen share. There we are. It is very cold in here.
I have the opposite problem. I'm steaming in here.
Oh, that sounds nice. Are you guys hot room people or cold? Cold. I keep my house at like 73 degrees. Is that bad?
I don't know. I'm still trying to find it. Like I either get too hot or too cold. Like
I like it hot, like super hot, steamy hot.
Yes, I'm with you. I am with you. Some people though, that's too hot. All right, let's talk about k-fold cross-validation. So we just talked about grid search, we talked about parameter searches, and we could just hand all of our data, blue. The question is here, what are we giving to these dots, to these parameters? What's the data set that we're giving to these parameters? And we could just give all of our data in our entire data set. The challenge there, the problem that we're going to run into, if we say what is the performance on all of this data, is we're going to run into the problem of overfitting. So overfitting, I don't think I have, do I have a definition for that? Nope. Okay, sorry. I should have a definition slide for that for you guys. Hopefully that's not blinking for you. Overfitting is when your model becomes too optimized to the training set. So this is our training set, but eventually we're going to want to put this model in the real world, and it's going to see different data. So if we're training a model to make product recommendations for customers, and we train it on a historical data set, I'm going to put real here, or like production. So if we're training a model to make product recommendations for a customer set, and we train it on historical data of customers who have purchased our products in the past, and customers who, and products that we've had in the past, then when we put this into production, it's going to see new customers, new products. They're not the old customers because we already sold to those people, or maybe it's the same customers and they're buying a different product. My point is that it's different information. It's different data. It's not the same data because that was in the past, that was historical data. When you implement something in the real world, it's going to receive new information, new products, new customers to make recommendations. And what we want the model to do is not to memorize the old customers and just memorize customer behaviors and become overfit to that. We want the model to make generalizations. We're going to talk about houses, for example. And let's say we train a model on all the houses in Elkhorn. We don't want the model just to memorize how houses in Elkhorn behave. Maybe we want the model to generalize to Omaha. So if we find the model that performs the best for Elkhorn houses, that may not be the same model that generalizes to the performance across Omaha houses. So we have invented, or the field of data science invented, a methodology to combat that. So we're going to talk now about k-fold validation. First, I realize we should maybe talk a little bit about training methodology. Let me see if I do it later. Yeah, that's fine. Okay, we're going to start with k-fold validation. So there's this whole, there's a paper, by the way, that was written, I don't know, maybe in the 70s or something, about the frog and the bird, and whether you start with, as a frog, you start with a concept and then you build to a broader picture, or you start as a bird, you start with a high level picture, and then we get down to the details. So we're going to be a frog right now, and we're going to start with one building block concept here, And then we're going to add concepts on top of that. So we're going to add train test split on this at the end. But for now, let's just start with k-fold validation. Let's try to ground and understand this. Okay, so k-fold cross-validation is a technique used to assess the performance of our machine learning model across different splits of the data. So we talked about, hey, we have this training data, which I'm going to call T, and we have this like real world information that is some theoretical thing that we don't know what it'll look like because we don't know what the stock market's going to do tomorrow. We don't know what the world's going to look like tomorrow. We don't know what customers are going to purchase our products tomorrow. What's a way that we can, so we only have access to T, but we want to kind of simulate training a model that generalizes to unseen data. That's the key word here. We want to train a model that generalizes to unseen data. So we can't make up the future and how data will behave in the future. So instead, we cleverly decide to develop a simulation where we take our training set and we split it into multiple data sets. Here I did 4 for some reason. So this is still the same data set, but we just break it apart into pieces. And then we can train a model over portions of that. We can say train over this portion and evaluate over this portion. And in that way, we're simulating what it would be to train a model over a portion of the data and then evaluate on another portion. So this is sort of our k-fold validation is sort of a simulation that we develop. It's a methodology really that we're employing to make sure that our model generalizes to unseen data. Okay, why is it called k-fold validation? Because k is the number of folds. So here I broke this down into 4 folds. So you could call it 4-fold cross-validation. Nobody really does that. They just call it k-fold validation. And then the parameter that you're setting is k. So typically the values that are chosen for this, by the way, that I see a lot, I see 3. If you have a really big data set, I see 5 pretty often, 7, 10. 10's a great number, but that's if you have a small data set, breaking it into 10 pieces is maybe not the best approach. So you're going to have really, really tiny pieces of tiny data sets to train your model over, and they're not going to be, it's going to be challenging for your model to actually learn anything with that small of a set of information. Okay, so these are kind of some of the numbers that I typically see. So look, we're going to walk through k-fold validation. I think it's really important that you guys, this is very much a core pillar of data science, of training models, of evaluating models. So we're going to walk through this in a similar way that we walked through the algorithms in the previous course. So we're going to break this down. It's going to feel kind of like overly explained, but I think it's very, very important. So we're going to break this down into 5 steps. We're going to walk through each step. The first thing that we have to do is we have to split the data. We're going to split the data into k equal sized partitions, k equal sized subsets, otherwise called folds. So that's why it's k-fold validation. Then we're going to do model training and evaluation on each fold. So we're going to do on each fold combination, which I'll talk about what that means in a minute. So we're going to train k times, and each time use k-1 as the evaluation set for the data set. So we'll have k different models. Then we're going to evaluate across each of them. Again, we have to choose a metric for evaluation. We're going to aggregate the performance. We're going to average across the folds. Kind of hard to explain without having the picture right now. But basically, when we break it down into these 3 folds, we're going to combine 2, evaluate on the 3rd, but we're going to do that 3 times. Combine the other 2, evaluate on the one we didn't use, combine the outside 2, evaluate on the middle one. And We're going to take the performance across each of those and then average it. So let's look at that. Let's dive into each of these in detail, and stop me on each of these slides if you guys have questions. So we have a data set. Suppose we have 30 samples, 30 instances in our data set, 30 customers maybe in our data set, this model that we're trying to build. The first thing that we're going to do in k-fold validation, we set our k equal to 3. And we're going to divide into 3 equal folds. Each fold is going to contain 10 samples. So we have fold 1, fold 2, and fold 3. The next thing we're going to do is model evaluation and training. So in iteration 1, we're going to run through 3 different iterations. In iteration 1, fold 1 is going to be our validation set. So these 10 samples we're going to set aside, and we're going to take fold 2 and 3 and we're going to smash them together, and we're going to train our model over fold 2 and 3. Then we're going to evaluate the model's performance on fold 1. So each of these folds has X and Y in it. So if we have house prices that we're trying to, I said these were customers, but now I'm going to make them house prices. If we have house prices that we're trying to predict, we're going to pass to the fit function of like a random forest or a logistic regression. If it's a regression problem, because house prices are scalar, we're going to pass X and Y. And the model is going to learn the parameters associated with X. We're going to set our hyperparameters. All of that happens in the fit model phase. And then we're going to call model.predict on fold 1. So we're going to call pred. Remember when you guys call pred, and here we go. You call pred and you get the predictions out of this on X associated here. And that's going to give you some probabilities, and we're going to compare that to the actual Y value, the Y true of these. And we're going to get some type of performance metric associated with that. So the orange box was not used in training, but was used in evaluation. The thing is, we're going to do that 2 more times. We're just going to shift which data set we're using, which subset of the data that we're using for evaluation. So iteration 1, fold 1 is evaluation, train over fold 2 and 3. Iteration 2, fold 2 is evaluation. We're going to smash together fold 1 and fold 3 and train over those. And iteration 3, fold 1 and fold 2 are used for training, and fold 3 is what we're going to evaluate over. Let me pause for just a moment. Any questions so far? I'm going to refill my water here. Okay. Someday you guys should do a bingo card and see how many times I say okay and so. You guys would, maybe that should be the free space. What's the point in evaluating over each of these folds? Why are we have an iteration, we're smashing them together, and we're going to get a performance metric here. We're going to get 0.7, we're going to get 0.8, we're going to get 0.6. Like, what are we doing with that information? How is that giving us value to split our data set into small pieces and train over each of these? And by the way, I want to emphasize that the training over each of these folds, when we say, hey, so we trained 3 models here. This was model 1, this was model 2, and this was model 3. And that was over one set of hyperparameters. So this is one set of hyperparameters. If we have like n estimators is 100 and max depth is 15, it's n estimators is 100, max depth is 15 for all 3 of these models. So different performance metric. Why is the performance metric changing? Why is this 0.7? Why is this 0.8? Why is this 0.6? What's driving that change? The data is driving that change. So the only thing that we're changing here is the subset of data that we're training on. Model 1 is fold 2 and 3 combined. Model 2 is fold 1 and 3 combined. Model 3 is fold 1 and 2 combined. So the only thing that we're changing is the data, and then that changes the performance on the model. The hyperparameters are the same. Of course, the parameters that the model learns, the weights and biases that it learns within the model, will be different because the data that we're providing it is different. So that's going to cause the parameters, the learned models that the model learns, the weights the model learns from data is going to be different because the data is different. Okay, so I wanted to emphasize that. Oh, look, I almost said the exact same numbers. Okay, so 7, 6, and 8. For each iteration, we're going to calculate the performance. So step 3 is performance evaluation. Again, what is the point of this? We're going to aggregate it. So we're going to take the average. We're going to take 7 plus 6 plus 8, and we're going to add them together, divide them by 3. So now what we can say is that our performance of our model, NE was 100. And MD was 15. Okay, so now what we can say is that the performance of our model when number of estimators is set to 100 and max depth is set to 15 has a performance of 0.6. Why are we saying 0.6 instead of 0.7 or instead of 0.8 or instead of adding all 3 of those folds together and just reporting the performance on all 3 of those added together? This is the average performance across each iteration. So when we break this model, this data set down into iterations and train the model on each of these subsets, we're creating that simulation of, we're creating that simulation of how does the model perform on unseen data. And you can see that the performance does change across these folds. So we're avoiding overfitting the model. This is going to enable us to generate a robust performance that's actually representative of that parameter combination that we're testing and trying. So 0.6 is a more robust or more representative performance metric of this combination of parameters. If we had just chosen this one or just chosen this one, that might not generalize very well. So this is going to generalize better, ultimately enabling us to select a parameter combination that does generalize better to unseen data. Okay. Let me pause here for just a second. Any questions so far before I move on to adding something to this? Okay, we're going to add to this. The final thing to do, I wish I had one more slide right before this. This is fine. So in our code, when we're building models, you guys have seen that we do train test split. So we'll say, we'll have the Y train, X train, Y test, X test equals train test split, pass your X, pass your Y, say how much you want to go into the test set. That line of code that we use using the sklearn train test split method. we're typically splitting our data set into two pieces, and that's modeling methodology. I want another slide here. This is fine. Okay. I'm going to do it on the whiteboard, and then we'll come back to this. Let's see. This wasn't, I want to be clear about this. Okay. It's kind of straight. Oh, it's my computer. That's good. All right. So we have our data set. Okay. Let's create a data set. Let's do house prices because I think we're pretty familiar with that. We have bedrooms and we have square foot. And we've got, these are our X features. So this is X sub 1, this is X sub 2. Remember, these are called features. And remember, this is called our target. And this is Y. And this is our house price. Great. So what we're trying to do is we're trying to create a Y equals beta sub naught, X sub 1, plus beta sub, I'm sorry. I did that last time too. Beta sub naught plus beta sub 1, X sub 1, plus beta sub 2, X sub 2, where that's going to be Y equals, this is our intercept, plus beta sub 1 is going to be our parameter that we're learning for bedrooms. Sorry, I'll put bedrooms times X, I guess, beta sub 1 bedrooms. Plus beta sub 2 square foot, okay? And these are our parameters, remember? Not our hyperparameters. Great. Okay, so we have this, let's put some data in here. We've got number of bedrooms. Maybe there's 2, there's 3, there's 2, there's 5, maybe an outlier of 10, and another 3-bedroom house. Square footage, we're going to go by thousands here because that seems easiest. Oh, we'll do 1,500. 5, that's going to be, maybe this is a 7,000 square foot house, and 3, 500. No, let me make this exactly the same for 1,500. Okay. Okay, and we have our house prices. We're gonna put house prices in Monopoly money because this is going to be 100. This is going to be 150. This is going to be 300, 500, 1,000, and 300 for some reason. Okay. We could just train over everything if we wanted to, but as we know, we want to. We're going to want to train, test, split this. So we're going to set some data aside, put it under lock and key so we can evaluate it. Because what we want this model to be able to do, we want to create a model that generalizes to unseen data. So if we give it 2 and 1,000, we want it to be able to tell us what the price is. If we give it 3 and 1,500, we want it to be able to tell us what that price is. We want it to generalize to that unseen data. So we're going to take all of this, and we're going to do train, test, split. Maybe we're going to do like an 80-20 split, something like that. So this is going to be our test set, and this is going to be our training set. And the only reason I wanted to write this on the whiteboard is because I wanted to write when we do that X train, Y train, X test, Y test is equal to train test split X, Y, 0.2, and then you have your random state. This is what we're talking about here. So that X train, Y train, that comes from this. So these are our X train are going to be our two columns here, and Y train is going to be our Y target variable. When we say X test, Y test, that comes from here. So we know that. We know that we do train test split, and that we break this into this piece and this into this piece, and we train a model over our training set, evaluate on our test set, and you guys are really familiar with that from methodology standpoint. That's great. That's great. What happens? And we even talked about cross-validation. So we know. So now we're getting to this picture. We're getting to the point. So we know that we have this training data set. And we know that we're going to, if we want to try a linear regression, and we've got some hyperparameters that we want to test across this, HP1, HP2, HP3, and we've got some set of hyperparameters we want to try. We know that we can take this training set and we can run cross-validation. Over linear regression by basically breaking this down into, let's say, 3 pieces. So we're going to take, 3 is weird here, but we're going to take this, we're going to break it down into a couple of pieces, give this to model 1, give this to model 2, give this to model 3, do that for each hyperparameter. Great. What happens if we have another model? Do that for each hyperparameter and we get some output of performance, right? So we get performance from CV, from cross-validation. Okay. The question is, what if we have another model? What if we have a random forest now? How do we choose a model? How do we know which model is performing better? We can do the cross-validation. We could run cross-validation over each of these, 2 different ones, and evaluate their performance in that cross-validation. Or we could just use our test set. We have a test set. Okay, we'll just evaluate on the test set. Well, what if we have another model that we're trying to do? What if we have model 3? What if we have model 10? And we keep using this test set over and over and over again. What's going to happen is we're going to select a model that performs best on the test set, and then we run into that problem of overfitting that we were trying to avoid in the first place. And instead of becoming overfit to our training set, now we're overfit to our test set because we keep using it and using it and using it. So I have a very opinionated methodology on this, which is that your test set is to be used once and only once, and that's right before you go to production, and then you squish everything together. So what do we do if we don't have a test set and cross-validation isn't going to be robust enough for us to do our apples to apples? You need something beyond cross-validation so that you can compare across models. But we can't use the test set because it's only to be used once for assessment of how the model will perform in the real world. Well, that's where we have a validation set, and that's what I had on the slides. And I need like 6 more slides in there. So we're going to switch back to that. Oh. Nope. Okay. The final step here is once we have this performance of how well the model performs across over these different folds. So remember, coming back to our analogy here, we have, here you go. Coming back to our analogy here, we have our training data set, and we have this fold 2 and 3, we're smashing together, evaluating on fold 1. Fold 1 and 3, we're smashing together, evaluating on fold 2. Fold 1 and 2, we're smashing together, evaluating on fold 3. Taking the average of that performance, and that's how we're selecting our hyperparameters. So the key thing here is that cross-validation is how you select your hyperparameters for your model. So cross-validation is how you select your hyperparameters for your model. Then we have a validation set down here. And when we evaluate on our validation set, this is separate from our training set. The validation set is how you select a model algorithm after hyperparameter selection. So let me go to the next slide because it shows where the test set comes into play. Putting it all together here, once we have a final model selected, final model, so say we had 3 different modeling algorithms, each with their own hyperparameters. We had linear regression, we had random forest. Let's say we had a XGBoost, which is a type of ensemble tree model that does very short, stubby trees. So we have 3 different modeling algorithms, and they each have their own hyperparameters. We're going to run cross-validation over each of those models and get a performance associated with each one from a cross-validation perspective. That performance is going to enable us to select the right hyperparameters for those models. Great. So we selected our hyperparameters for each model. Now we have 3 models with set hyperparameters trained over our entire training set. How do we know which one is better than the other? We apply each of those models to our validation set, our 20 samples here, and it turns out our random forest was the winner. Our random forest outperformed XGBoost and it outperformed linear regression. So we pick the random forest, and then here's where my opinionated perspective here. Once you choose the random forest, smash together the validation set and the entire training set. So the training set had 30 records in it, 30 samples in it. The validation set had 20 samples in it. Smash them together. We now have 50 samples, a 50 sample data set. Retrain over the random forest with the hyperparameters selected. Evaluate on the test set. That is your best assessment for how this model is going to perform in the real world. So we evaluate over that test set, smash together that test set, the validation set, and the training set again. Retrain that same model over those hyperparameters. Yes, the performance will change. No, we have no way of evaluating that. Put that model into production. So the model your best estimate for how the model is going to perform in production is how the model performed on the test set, even though you then after that added that test set data to your overall data set for final training and pushing into production. Let me see if I have any slides that explain this better. Let me pause for a second. I feel like that's a methodology piece that I should have a few slides on here, and I kind of just said it all verbally. Maybe I have it on the slide. I think the key thing I want you guys to take away here is that k-fold cross-validation is used for selecting the hyperparameters associated with your model. So we apply k-fold validation. We're using it to select our model's hyperparameters. Then when we're applying validation, our validation set, we're using that to choose which algorithm is the more performant algorithm after selecting hyperparameters for that algorithm. The test set, the test set has one purpose and one purpose only, and that's to provide an assessment of performance when you put this into production, to provide a final assessment of performance in terms of how this will generalize to unseen data. So the test set has one job, and that's for you to be able to say, I stand behind the metric that this will have an 80% performance when I put this into production. Excuse me. The downside here to k-fold validation, which I don't think I emphasized, but I need to here, I probably should have, is the number of models that we're training. So it's expensive. It's computationally very expensive to run k-fold validation. So here we have 3 models for every hyperparameter combination that we are performing, that we're running. So if we have, let's go back to our hyperparameter 7. We had hyperparameter 1 and we had 7 different values we were searching over for this. Hyperparameter 2, let's say we have 2 values we're searching over for this. And hyperparameter 3, let's say we have 2 values that we're searching over for this. Remember, we said 7 times 2 is 14. 14 times 2 is 28. So we have 28 different models that we're training. Once we apply cross-validation on top of that, we take 28 times 3. So if we do 5-fold cross-validation, we take 28 times 5. If we do 10-fold cross-validation, if we have a lot of data enough that we could actually do 10-fold cross-validation, we take 28 times 10. So now we have 280 different models that we're training. It's very computationally expensive to do cross-fold validation, especially for large data sets or really, really complex models that take a long time to train. It may take quite a bit of time to train just one model. If it's a complex model, you have a large neural network that you're training a lot of back propagation going on. That's going to be much more computationally expensive than a really simple linear regression model. And if it's a large data set, it's going to take more time to find those parameters to reach convergence. So when the algorithm is searching over what those parameters should be, it's attempting to reach convergence, and that takes time. So if you have a really large data set, it may take it may take longer to converge on your parameters. So it's not necessarily suitable for all scenarios. You might have to make a really tough choice and decide not to do k-fold validation if it's too expensive for you computationally. And so that's a choice that you will have to make. Another thing to note here is k-fold cross-validation is not sufficient when you look at time series data. So if you're working with time series data, you're going to need to use time series cross-validation to make sure that you're not data snooping. I'll give you an example here. I think this is the example slide I wanted to talk about. Every year, it seems like, I see it less often now, but for a long time, every year, somebody would come out with a model that they said, I have created a model that predicts the stock market. It seems like it happens every year. And somebody says, I have an F1 scribe in accuracy. My performance is 0.99. Here's my model. Here's my methodology. Look, it performs really, really well. And I did train, test, split. I did cross-validation. I did this testing. And what happens is people do this train, test, split, but not from a temporal perspective. And so they'll just train, test, split, and put Apple stocks in the the test set and Google stocks in the training set, and they'll train the model. The thing that happens with the stock market and any time series data you're working with really is things will influence other things. So when Apple goes up, there's a trend that other things go up as well. The market goes up or the market goes down. So there's a correlation there. And so what these models are actually doing is they're saying, well, I know that everything else went up on this day because I saw that in the training data set. So you're asking me to make a prediction on the Apple stock. If I just look at that day, everything else went up, I'm going to make a safe bet that it's probably going to go up. But in reality, when we actually put these models into production, we don't know what tomorrow is going to look like. We don't know what 80% of the stocks are going to do tomorrow. It'd be great if we did. So that is something called data snooping. It's a really particular mistake that is sometimes made when training a model. So if we're looking at temporal data, train test split is not enough. You have to do time series train test split. If you guys were here, I'd whiteboard it. It's really similar to this, but it's really similar to, am I not sharing? No, I am. It's just not. There we are. It's really similar to this same methodology. We're splitting into validation and test sets, but now we're just going to consider a temporal element to it. So when we're creating our holdout set, there's going to be an element. It's not going to draw perfectly on here, but there's going to be an element of us holding out time here. And then also holding out records. So when you create your test set, it has to be something called an out of time, out of sample set, making sure that you're withholding time from everybody equally. So basically what you're going to do is you're going to create a fake cutoff time in your data set, and you're going to pretend that the world ended at that point, and we know nothing else about the world after that. And then from that, you're going to hold out. You have to hold out samples as well. So you also have to hold out, Apple stock. So your model's never seen that before. So you'll have a out of time, out of sample set. So very important. Methodology is important to make sure that we're creating models that generalize to unseen data. We're making models that are not overfit, which are two sides of the same coin, really, and ensuring that we're not data snooping. Okay. I have break here, but I also see that there's only 2 more slides here. So let's just talk about this slide here. Model considerations. We want our model to perform well and to generalize to unseen data. We want our model to be robust. So one thing to consider is to be perhaps curious about or questioning or concerned is if you're doing this cross-validation and we're seeing that on one of these folds, for some reason, our performance was like 0.3, and then on this one, it was 0.9, and then on this one, it was 0.4. Like this is concerning. Like that's a lot of fluctuation just from changing the data. So there might be something to look into, to investigate there. That's not a very robust model. That's a really flimsy model, and averaging those performance metrics may not necessarily help us. A model parsimony is something that you should look at. It's looked at a lot statistically in terms of how good of a fit is your model. Are the features that you're putting into your model informative? So we talked about model parsimony when we were talking about the R-squared metric and the adjusted R-squared metric. Those are metrics that are used to evaluate model parsimony. Are we adding extraneous features to our model that aren't adding a substantial amount of value in the predictive output? Another consideration is computational complexity. So these are criteria for like, how do you choose your model? Another consideration is computational complexity. There may be certain reasons why you need your model to be more explainable, to be able to explain the model more. talk about feature importance from a random forest, talk about the actual weights, the bias variables that come out of linear regression. Whereas when we get closer to the realm of neural networks, we're kind of losing a little bit of that interpretability, that explainability from our model. Okay. Any questions thus far? I'll keep the annotations, share those with you guys in the Google Drive, as always. That was all I had for lecture today. However, I do have notebooks for us to work through, so let's do that. And I'll give you guys some notebook time, and then we'll talk about them. So if you go to our student folder, and we get a model selection and cross-validation. There are 2 notebooks in there if you guys could download those. One is K-fold validation, and I'm downloading them and moving them now, and the other is hyperparameter tuning. Okay, I think this one's mostly just some example code on K-fold validation. And then we have our hyperparameter notebook. And I think this is probably where we'll spend most of our time. I think we'll dig into hyperparameter tuning here a little bit. Okay, let's take a short break / look at the notebooks. Spend maybe 10 minutes on break / look at the notebooks, and then we're going to come back. We'll briefly talk about K-fold cross-validation, but really I want to talk more about the hyperparameter tuning, and I want to get into this code a little bit and show you guys how to actually use grid search CV. That's what I want you to take out of this. How to use grid search CV to actually search over these hyperparameters. So I think you guys understand it from a theory and concept perspective. Let's look at the actual code. And then I want to show you how to get the best model out of your grid search CV, how to interpret the cross-validation results, how do you actually use this information to generate that best model. So spend 10 minutes looking at these and playing with them maybe a little bit, and then we'll come back and we'll just walk through this. So 32. All right. I'm going to actually move. Let's just do the. Sorry. Let's just do this one. I'm going to move this over to the screen. This will be easier. And share this window. All right. Let's talk about hyperparameter tuning. So what I want you guys to walk away with here is how to actually apply a grid search to your model. So you guys are very familiar by this point with how to build your model, how to train a random forest classifier here. Let's walk through an example. Okay, we're going to load the iris data set. You guys remember the iris data set? We have sepal. Let's do X. Let's look at X. Let's look at Y. Great. So we have different species of flowers that we're trying to predict. This is already encoded for us. So instead of the actual labels, we have 0, 1, and 2. And then we have these features associated with it. So the sepal length, the sepal width associated with each of the flowers. And then we have an outcome here. So we're going to train test. So we're loading that from the iris data set. We're going to train test split. So we're going to do our X train. This is what I was talking about on the board. We have our X train and our X test. So we're doing train test split. And then we're going to instantiate a random forest classifier here as our model. If we wanted to do train test validation split, what we would have to do here is actually split again. So we'd have to do X train validation, Y train validation, and we would pass the X train validation, Y train validation, and this would be our X train X validation, Y train Y validation. Okay. All right. But let's keep things simple. Let's not worry about that. Let's go back to our X train, our train test split. We're just going to keep things simple, keep them simple, stupid here. So we have train test split. And we have our model and our random classifier. And you guys know that if we wanted to do this sort of the traditional way, that we could, without doing a grid search over all these different model parameters, we could do model.train, and we would pass X test, or I'm sorry, model.fit, and we would pass X test, and then we would do model.predict, and we would pass, I'm sorry, X test, X train, Y train. It's late. And we would pass X test. And these would be our Y preds equals. And then we would have our true values. And we would do something like accuracy of Y, Y test, Y preds. I hope I got that order correct. And we should probably import accuracy from sklearn.metrics. Yeah, import accuracy score. Accuracy score. We don't need to wrap that. See, the generative AI stuff does weird things sometimes. This is useless. It's just creating, all it's doing is renaming accuracy score to accuracy. So it's taking in Y true, Y pred, and this is a wrapper. It's wrapping the accuracy score, completely unnecessary. I have a theory, by the way, that if you guys look at code bases here in the next 5 to 10 years, they're going to be just full of all this like unnecessary, ridiculous code, and it's really going to be a problem. And it's going to compound on itself because then it's going to learn from that. It's going to be very interesting. Okay. So perfect accuracy score. Interesting. Okay, that's fine. So if we wanted to train a model, that's how we have been doing it up until this point. Now, what if we wanted to change the N estimators? So let me bring down. So what if we wanted to change some of the parameters in here? So we have a random forest classifier. What if we wanted to change N estimators to be 100, and then we wanted to see how it performs? Then we wanted to change N estimators to be 50 and see how it performs. Let's see if it changes with 200. I'm probably doing something wrong here in the... One second. It is Y true, then Y pred. Oh, I did do that right. Okay, whatever. It's a very small data set here. So N estimators equals 200, and we're still happening to get an accuracy score of 1, which is fine. But what if we want to add in max depth here? Sorry. And we want to make max depth 10. And then we want to see how that performs with 100. We could keep doing this. We could keep adding parameters and like doing all the combinations and rerunning it. But that's a lot of work. That introduces room for error. We could make human mistakes. That's really manual. It's not systematic. It's not robust. And also it's just kind of annoying. What's a better way to do that? Let's leverage a hyperparameter grid search. So this is what we were talking about. This is how we would codify this. We're going to leverage something from sklearn called grid search CV. You can look this up in the sklearn documentation. And grid search CV is going to take a estimator. So it's going to take our model, a random forest model, any model. We can even just say, I don't want to confuse. Here, it takes a random forest model. It's going to take a parameter grid. So you have to tell it what to search over. And the parameter grid is this here. And you have to do it in this syntax. It's a dictionary. So key value pairs, as you guys know. N estimators. So the key is the name of the parameter as defined in the sklearn documentation. And the value is a list of parameters to search over. So try 50, try 100. So here we have 3 values that we're trying for N estimators, 3 values that we're trying for max depth, and 3 values that we're trying for min sample split. So 3, 6, 9. So 3 times 3 is 9, and then times 3. So there's quite a few models that we're going to train here. Okay. I called this the wrong name. Random forest classifier. Okay. There we are. All right, so we're estimator that we're passing to the grid search CV is going to be a random forest classifier, and we're passing a parameter grid here. CV, this is our K. Remember, K-fold cross-validation. Grid search CV is synonymous with K-fold cross-validation. The number of folds that we're doing here is 5, which is probably way too many for this data set. We should do 3. It's a really small data set. Let's look at how small it is. Length of X, 150. Really, really tiny data set. We're going to score just based on accuracy. Let's change that to F1. I think I didn't run parameter grid. Okay, that is the name for that metric there. So we have a grid search instantiated now. So grid search Here we have a grid search CV. It's a grid search object. Remember, everything in Python is objects. So we've taken the random forest classifier object and put it inside of a grid search CV. And now there are, I have to cough, I'm so sorry. So we took the random forest classifier and put it inside of the grid search CV object. So now we have a grid search CV, but this isn't fit to anything. Like we can't make predictions on this yet because we haven't trained the model that exists inside of here. What's great about sklearn is grid search CV uses the same methods and the same functions, the same structure that you're familiar with for all your other models. So grid search CV kind of acts and behaves like a model itself in that it has a fit function. So all we're going to do is call grid search.fit. We're going to pass xtrain, we're going to pass ytrain, and this is now a fit model. So let me run this. Ooh. Oh, I think we're going to get some errors because our data set is so small. It's going to cause a problem, basically. But let's see. Okay. So now we have a fit grid search CV. So this is fit now, a fit grid search. And what we can do is we can get the results. So we can call grid search.cv underscore results underscore. And we can put that into a data frame. So it kind of looks like a sort of Excel sheet. And we can get a lot of information out of this. Mean fit time, how long did it take to fit? Standard deviation of the fit time, like what was the deviation in the fit across the different folds? Mean score time, standard deviation of the score time, the parameters that were selected that this was trained over. So here are the parameters, and then the performance, of course, and the rank score. So we can get mean test score, and then we're going to get the rest, or the rank test score. So this is where you're going to get all of your information. What's great about grid search as well is it will just tell us what the best parameters are. So we don't have to keep changing the parameters, write down on a notebook off to the side. I tried 105 combined, and then it had a performance of this. It'll just run all of this for us, do those calculations, output, here's our best hyperparameters. So in our case, it was max depth is none, min sample split is 2, and estimators is 50. When we look at the end of the day, what we want is the best model out of this. And the grid search has a function called best estimator that will just pull the random forest classifier out. So when you call grid search, excuse me, when you call grid search.bestestimator and we run type on this, I know you can see it there, but we're just going to be explicit about it. This is actually a random forest. So if you need to implement your random forest into production, you need to pull that out to put it into production. You can call grid search.bestestimator. Okay. I think that's it for today. Any questions? Great. I'm going to stop the stream and then I'm going to ask that again.